In this example, we're going to look at the integration of a product of a log function with a trigonometric function, a sine or a cos function. In this example, we look at the sine function. The method is the same if it was a cos function. So once again, we have our formula up above, integration by parts. So we need to, first of all, identify u and dv, and then we need to from that, we need to calculate du and we need to calculate v. So du is here and v is there. So once again, we go to our table, and the rule is if one of the factors is a log function, that must be taken as u. So we say u is equal to the log of x, and dv is everything else, so it's the sine of x dx. So then what we do is we differentiate the u, so du dx is 1 over x. So that implies that du, which we need for our formula, is dx over x. On this side, what we do is we integrate both sides, because what we're looking for is v. And the integral of sine x is minus cosine x. So we have everything we need to plug into our formula. So our formula is u dv. So we need u is the log of x times v is minus cosine x. And then that's minus the integral of minus cosine x times dx over x. So that's for du basically. So if we look at this, we have u v minus the integral of v du. So we plugged everything in there, and that gives us minus the log of x times the cosine of x minus the integral. Now we have a minus times a minus giving us a plus, and that is the integral of cosine of x divided by x times dx. This cannot be integrated. No direct integration. Therefore, we're going to have to do the same step again as we did for the other function, which is to use the Maclaurin series. So it's going to be an approximation rather than exact solution. So what we then do is we look for our Maclaurin series for cosine of x. And the Maclaurin series for cosine of x is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And there's a general formula here, minus 1 to the power of k times x to the power of 2k over 2k factorial. That's the general formula. You don't have to worry so much about that. So if we then take every term there and divide it by x, cosine of x divided by x is 1 over x minus, and we divide this one by x, so it's x squared divided by x is x, and 2 factorial is 2. Then this one is x to the 4 divided by x is x cubed. 4 factorial is 24. And then we have minus x to the power 6 divided by x is x to the power 5. And 6 factorial is 720. And so on. So what we're going to do is integrate that. So cosine x divided by x is the integral of 1 over x dx. So I need a dx there. Minus a half times, I'll take the 2 out here, x dx. Plus 1 over 24th, I'll take the 24 out, x cubed dx. Minus 1 over 720 times x to the 5 dx, and so on. I'll just use that many terms. So the integral of 1 over x, of course, is the log of x. Minus a half times the integral of x is x squared over 2. 1 over 24. The integral of x cubed is x to the 4 over 4. Minus 1 over 7/20 times x to the 5 is x to the 6 divided by 6. And so on. So if I go and do those, I have log of x minus x squared over 4 plus x to the power of 4 over 96 minus x to the 6th over 4320. And I'm just going to put in one that I worked out earlier, x to the 8. I haven't shown how this worked out, but it would be basically 322 over 516. The reason I'm showing that is this value is so large that this x to the power of 8 is a large number as well, depending on the value of x. But basically, it's a very large number, and these numbers will start to go down towards 0. So my full integral then, if I take these terms here, is the integral of, go back up to the top, it's the log of x times sine x dx is equal to, I can take this term here down. So it's minus the log of x times the cosine of x plus, and then I can just open up a bracket and I can insert everything in here in place of cosine of x dx. So if I just take everything here, so it's the plus the log of x minus x squared over 4 plus x to the 4 over 96 minus x to the 6 over 4320, and so on. So you could go on to infinity with all these terms, but you'll find that after a certain number of terms, your answer should be accurate enough. Okay, that's that one completed.